All right, we are a couple minutes past 7:30. Let's get the show on the road. Good evening or good afternoon, depending on where you are, Olympus colleagues and valued urologist partners from around the U.S. Wherever you may be right now, thank you for making this exciting event part of your day. My name is Brian Schneider, and I'm joined here by Mike Rondinelli. Together, we are your hosts for this evening's webinar. We are Olympus product marketers managing the commercial launch of the SOLTIVE SuperPulsed laser, the world's very first thulium fiber laser for the treatment of renal calculi, BPH, and other soft tissue indications. Before I introduce our speaker, Dr. Knudsen, I have three brief announcements regarding this webinar. Number one, we anticipate many viewers, over 200 RSVP this evening. So due to the extensive size of this virtual audience, we will have everyone on mute for the duration of the call except for myself here, Mike Rondinelli, and Dr. Knudsen, just to ensure the best viewing experience for everyone. Number two, this event is for 1 hour. The presentation content, which includes multiple endoscopic video of SOLTIVE, should take approximately 40 minutes, followed by a question and answer session at the end. If you have a question, please use the Q&A chat feature on the software display. This is located in the bottom right-hand corner of the software display. If you're in a dinner event with an Olympus host, please have them input this question for you. During the video playback, we may have an opportunity to cover questions as we go, so please enter your questions as we progress, and we'll get to them. To encourage engagement, all questions from the audience will remain anonymous. Number three, if you need to depart early, rest assured we will be recording this digitally and distributing it after, so you won't miss any of Dr. Knudsen's thoughts or content. So with all that out of the way, let's get to why you're all here tonight. This evening's speaker has been a U.S. board-certified urologist for 14 years. During this time, he's been a highly valued fixture in the U.S. and international academic urology community, helping to meaningfully advance urology medicine. He has contributed to over 70 publications in major urology academic journals, with most of this content comprising of clinical or bench data focused on kidney stones and their surgical treatment. This goes along with countless abstract presentations and professional speaking engagements at high-profile conferences like AUA and WCE over the last decade. He has multiple current appointments as part of his practice, the most relevant being Director of the Comprehensive Kidney Stone Program at the Ohio State University Wexner Medical Center. I present to you one of the world's foremost experts in kidney stones, Dr. Bodo Knudsen of Columbus, Ohio.
Thank you very much for that very kind introduction. I'm definitely very excited to talk about the SolTIVE SuperPulsed thulium fiber laser tonight. Been involved with some of the projects with Olympus for a few years now, and we were fortunate enough to be the first site at the Ohio State University to use it clinically last year, so we've got a lot of hands-on experience with it. I am a consultant for Olympus, and we have the disclaimer posted here regarding this. And then I am also a consultant for Boston Scientific, so please take that into consideration as we go through this presentation tonight. So we all know that the Holmium YAG laser has been the gold standard for really about the last 20 years. It's been a very good laser and has served us well in urology. And there's been some refinements of it over these years, but the reality is there are some inherent limitations of the technology, and I think we're really pushing up against the ceiling of that. And it's really the thulium fiber laser now that is looking like it may be the potential successor to the Holmium YAG and able to overcome some of these inherent limitations. So what are the limitations of the Holmium? Well, we know just by looking at it that it's a big box that has a huge cooling system in it. So they have a liquid cooling system that requires a lot of power. The Holmium YAG typically, for the high-powered versions, require 30 or 50 amp service, and that can be difficult to install in your operating rooms depending on your electrical setup. The systems are big and difficult to move around, so they're not really very portable. And then on top of that, they are quite fragile, and that has to do with the mirrors that are on the inside. Another limitation that we discovered some years ago when we did a lot of laser fiber testing is that there is a multimodal spatial beam profile. And basically what that means is this laser does not work very well with small fibers. So as soon as you get into a tapered fiber, anything less than about a 240 micron core, you have to really try and funnel that energy into the core of the fiber. And when you do that, you start to see a lot of problems with the fibers on the Holmium. There's been a few very small fibers that have been tried, such as a 150 micron core. And they simply just don't work well. They tend to fail at the connector. So that's a big limitation that the Thulium can potentially overcome. The other limitation is how quickly you can deliver those pulses. So the best case scenario with a P120 Moses laser is about 80 hertz, so 80 pulses per second. And this has to do with the fact that that's a multi-rod laser, but each individual core is only capable of about 30 hertz at the max. So you really hit this sort of ceiling where going up to roughly 80 hertz is the most you're going to get with the best technology out there right now. And then the final big thing, and this is something maybe gotten used to some degree, but is still an issue, is how loud it is. Anyone who does stones at high frequency knows how loud those lasers get. It's disruptive in the operating room. It's hard to hear people. And that's, again, it's just a limitation of that large cooling system. One other point, and I'm not going to dwell on this too long, I just want to make it as clear as possible, is the Thulium YAG laser has been around for a while. It's been used in urology for a while, and it is a completely different laser than a Thulium fiber laser. They are not comparable really in any way, so it's important because sometimes there's some confusion. People hear Thulium and they think it's the same, but they are completely different technologies, really not relevant to each other at all. So how does a Thulium fiber laser work? What makes it tick per se? So it's a much simpler design than a Holmium, and it's basically a long, thin fiber that's inside the laser. So when you look at that diagram from the reference I cited there, that square box is basically the inside of the laser. So there's this long, curled up fiber that's doped with Thulium, and then a diode laser is used to activate it. And when the diode laser is activated, then a 1920 nanometer laser wavelength is emitted, which then goes into your fiber that's connected to the box. And they're really standard silica type fibers, similar to a Holmium YAG fiber that will deliver the energy. The advantage of this setup is it's much, much more efficient than how a Holmium YAG laser works. And this allows it to operate at high power, but use a standard electrical outlet. And that's something we'll touch on a few times tonight. So standard electrical power for the Thulium fiber laser. The design is also pretty robust, so it's going to be, or it should be, more resistant to moving it to shock, and it also allows the unit to be very small. So a lot of this has led to sort of the promise of Thulium fiber laser. That you've got this highly efficient design that can be moved around, and now it's capable of extremely high frequency. 2000 hertz and maybe even above that is what it can reach, as opposed to 80 hertz with the Holmium. And this got us very excited, especially when we started doing some of the early work. And this is an example of lasering a stone into fine dust in an animal lab we did early on. So here's how the system really looks. This is the SolTive SuperPulsed Thulium fiber system, and you can see it's on a standard cart. Looks like there's a shock pulse device on this cart as well. So it's about the same width. I kind of equate it to a laser printer. It's kind of how it looks, or a home theater PC. it's easy to position, it's easy to move around, and as soon as you start using it, those are the things not only you notice, but the staff in the room notice how much easier it is to get this in position as compared to the big Holmium lasers that they're used to using, and that it has that nice touchscreen interface. But the big one for me is the air-cooled operation. So it's got the vents and the fans on the inside. If you look at them, it kind of looks like the same fans you have on your PC. And again, they're pretty quiet. They spin, they move the air, and they cool the unit, but you really don't hear them in the operating room. So you'll be in there working on a big stone, and you just don't have that loud noise that you get in systems. So just to take us into a little bit of laser physics, traditionally stones have been thought to break up by photothermal ablation. And Joel Teichman, when he was in San Antonio, did a lot of the pioneering work on this. And they tested the Holmium YAG laser at the time because there were people debating exactly how stones break up. And at that time, they felt it was a predominantly photothermal mechanism. So the laser energy is absorbed by the stone, and it causes the stone to melt, to decompose, and eventually break down. And that's how the laser lithotripsy works. There's perhaps a little bit of a weak photoacoustic mechanism, and that's kind of partly what gets the stone bouncing a little bit as well, but it's really a very small part of it. Really, it's primarily photothermal ablation. And this has kind of been the theory that people have held for the last 20 years. When you look at the wavelength of the thulium fiber laser, so when you look at this chart here, you can see that the wavelength is less than the Holmium YAG. So the Holmium YAG is about 2140 nanometers, and the thulium fiber laser is about 1920 nanometers. And what the big difference is, and why that red line is going up there, is the thulium fiber laser is more highly absorbed in water than the Holmium YAG. And that's important for a couple of things. One is just simply the safety aspect of it. We work in a fluid environment, so having your energy absorbed by water is a good thing. But we also think that it's tying into one of the reasons why the thulium fiber is more efficient at breaking up stones compared to the Holmium YAG. So this slide shows one of the additional mechanisms that breaks up stones. And this is by basically little micro explosions of water in the stone. So we know that different stones have different amount of water content. But when you laser stones that are wet, you see improved efficiency with the thulium fiber laser. And it's thought because it's so highly absorbed in water that it really works on this mechanism to help break down these stones more quickly. So with sort of the early results coming out of the thulium fiber laser, there's been a lot of questions raised. So you have this high frequency laser, seems to work really well for stones, but how much heat does it generate? That's been one of the concerns. How well does it really dust, and does it really fragment stones? What about retropulsion? You know, that's a big issue clinically when the stone is moving and bouncing around. You don't want to be chasing it. So how well does the thulium work in that regard? And how about laser fiber burn back? We all know it's kind of a pain when your fiber burns back during a case and you have to stop and strip it. Sometimes that can slow you down. Worst case scenario, if there's bleeding or something, you might lose your vision. So these are all important factors. So really a series of experiments were designed to try and look at some of these questions and come up with some answers. So these studies that I'm going through were presented either at the AUA or at the World Congress, and they looked at some of these questions that we raised. So the first one was temperature rise during laser lithotripsy. We compared the SuperPulsed thulium fiber laser with the P120 high-powered Holmium and went to see if there were differences in temperature. So when you look at this graph, focus first on the left side. So that's using dusting settings. So comparable settings, so on a Holmium YAG for dusting, typically 0.3 and 70 would be a typical setting that's used. And then on the SuperPulsed Thulium fiber, the SPTF is the SuperPulsed Thulium fiber, settings of 0.1 joule, so a lower energy at 200 hertz was used. And at those settings, we can see that there was a rise in temperature in both, slightly more rise on the Holmium side, but clinically less than a degree difference. So I would say clinically an insignificant difference. So they both essentially went up the same. Now that solid line across the screen is 42 degrees Celsius. And that's important because above 42 degrees is when you start to get cell damage. So it takes a prolonged exposure at 42 degrees to get cell damage, but that's where it starts, where you start to denature proteins. So ideally, you want to keep it below that. The right side shows fragmentation settings. So 0.8 joules at 8 hertz, there was, again, a rise in temperature was slightly more with the thulium than the holmium, but again, within 1 or 2 degrees, so likely clinically kind of an insignificant difference. So very similar rise that you see there. And in this case, it's quite a bit below the 42 degree threshold. Along with the temperature measurements, this study also looked at pig ureter. So firing the laser at these settings in the lumen of the ureter and then looking at some histology after. And really to summarize this, at all settings tested, there was really no difference between the holmium and the SuperPulsed thulium in terms of any histologic damage to the pig ureter. Really, there was no damage with either with operating the laser properly. So what you can take away from this is it's actually your power settings that are important. So whether the power comes from a holmium laser, whether it comes from a thulium fiber laser, it's going to be how many watts you're putting out from the laser fiber. That's what's going to raise the temperature. So watts are watts. So it's really comparable. So can you get into dangerous temperatures? Sure, you can. You can with the holmium, you can with the thulium. So you have to be mindful of your settings and where you're working. But if you're using appropriate settings and if you have appropriate irrigation, you're going to be safe, which has been well established with the holmium and would also apply to the thulium. So it's really, I just consider it the same. The next study looked at how well the laser dusts and fragments. So how well does it ablate stones? And again, it was a comparison of the SuperPulsed thulium with the P120 120 watt laser. So in this experiment, there's a lot of pictures here, but really what it was there were square Bago stones that were 125 millimeters cubed. So exactly the same size. And then there was this kind of box created that had a sieve underneath, and there was a couple of different sieves that were used depending on the setting. And then the laser was activated for a fixed amount of total energy. So for the dusting settings, a total of 2 kilojoules were delivered, and then whatever was broken up fine enough to make it through the sieve was measured. And then on the fragmenting one on the far right, a little bit less energy was delivered, only 0.5 kilojoules. And the reason was anything more than that and the stone was completely gone. And then bigger holes were made for that. And then we measured how big the fragments were and how many fragments passed through. And those holes were about 3 millimeters. So these pieces had to be down to at least 3 millimeters or smaller to fit through there. So let's look at the graphs here. So let's go first on the left side of the screen. These were the fragmenting settings. So fragmenting with the holmium was 0.8 joules at 10 hertz, with the thulium was 0.6 joules at 30 hertz. And at these settings, what we found was that the ablation rate was higher with the thulium. Not a huge difference, but a little bit better. And then on the right side, we looked at the dusting setting. So a typical dusting setting with the Moses laser was 0.3 joules at 70 hertz. And then the dusting setting used on the thulium was 0.1 joule at 200 hertz. And at those settings, again, you could see that the thulium was quite a bit more efficient in terms of ablating the stone. So both fragmenting settings and dusting settings, there was an advantage for the thulium. So this slide is interesting because it shows a couple of different things. So the first thing it shows is that at fragmenting settings, there was an advantage, which we also saw on the last slide with the thulium. But so that's the graphs. Now you'll see some numbers on the graphs. It says 7.2 for the holmium and it says 2.1 for the thulium. What this was how many pieces greater than 2 millimeters were there. So on average, there were 7.2 pieces more than 2 millimeters with the holmium versus 2.1 pieces greater than 2 millimeters with the thulium. And it was interesting when we kind of looked at this because later when we started using it clinically, we saw a correlation. So what that means is the pieces with the thulium, even at fragmentation settings, were smaller. And this kind of gets back to this concept that it's truly a dusting laser. But also, if you're going to basket, the ideal is to have less big pieces so that you don't have to make as many passes with the basket. But where we really started to understand this was when we used it clinically. And when I started to treat some big stones, especially with mini perk, I was finding that I wasn't getting big chunks of stone. I was just getting all this small grit and small rubble, and the fragment size was very consistent. And I think this is a pattern that as you start to use this laser, you're going to see the pieces that are created are very, very consistent in size, and you don't get too much of the scenario where you're hunting for big pieces amongst the small rubble, which you often get with the holmium. You're often digging through trying to find those pieces that aren't going to pass. The consistency of the fragment size is really interesting with it. All right, so the third set of experiments was set up to look at both retropulsion and laser fiber burn back. So both important kind of clinical issues that we wanted to address. So this is the setup for the retropulsion experiment. So you can see here, zoomed in on the right, you've got a laser fiber coming down and putting pressure on a stone, and then underneath that stone is a plate that measures the force that's being put on it from the laser energy that's being pushed through the laser fiber. So that's how we could measure force, and we could measure it per pulse, and we could also measure it over time. So let's focus first on the left side, okay, on that first graph. So these graphs are looking at the retropulsion over 1 second. So how much force per second there is, okay? And that's important because if you're running the thulium at high frequency, you're going to have lots of pulses in that second, and that's going to be clinically relevant. So that's why we wanted to look at it first over time. So when you look at dusting settings, so 0.1 joule and 200 hertz, which is the SuperPulsed thulium fiber graph, that's the first one. The middle graph is 0.3 joules, 70 hertz, long pulse mode on the holmium. And then the third graph is 0.3 joules, 70 hertz in Moses mode. So we looked at both long pulse and Moses mode with dusting. And with that, you could see that the retropulsion was very similar. There was no difference between the thulium fiber and the Moses, but there was less retropulsion with both of them compared to the long pulse Holmium. So if you've used the long pulse Holmium, you can get a sense of how that works. So both the Moses and the thulium were better than the long pulse. When you looked at fragmenting settings, here we only tested long pulse with the Holmium, and we looked at the thulium. We did not test Moses mode here. In this one, the retropulsion similarly was quite a bit less with the thulium. So that was over time. Now, if you look on the right side, we are looking at retropulsion per pulse. So with each pulse that's delivered, how much of a difference is there? And the results were pretty similar, but a little bit more dramatic, which is what you would expect since the thulium is normally operating at such a high frequency. So you can see there's very little retropulsion with the thulium at 0.1 joule setting. And then with the Moses laser, there also is very little retropulsion. And then with the long pulse Holmium, there's quite a bit more retropulsion. And then this was even more pronounced when you looked at the fragmentation settings. When we used fragmenting settings, there was way less retropulsion. So as you go up on that energy, it seems that that difference is more pronounced. So this is the setup for the laser fiber burn back. So basically what you're looking at, really focus on the right side of where those two pictures are. On the picture on the top, you've got a laser fiber that's new, that's got a nice long tip on it, how when you take it out of the package, that's how it's going to look. And then after it burns back, it starts to look more like the one on the bottom. So we did a set of experiments where a set amount of energy was delivered through the fibers, and then we looked at how much they burned back during this process. So let's kind of walk through, because there's a bunch of different settings that we tested. So the first one was dusting settings again, so 0.3 joule, 70 hertz long pulse versus 0.1 joule, 200 hertz on the thulium. So the red bar is the Holmium, the blue bar is the SuperPulsed thulium fiber laser. So at dusting settings, you can see that there is not a lot of burn back with either, but there is definitely less burn back with the thulium. Then we go to the next graph, low power lithotripsy, so 0.8 and 8, pretty typical fragmenting setting for the Holmium, short pulse, and then 0.8 and 8 on the thulium. So again, pretty big difference in terms of less burn back with the thulium. Going up in the energy a little bit to 1 joule, a little bit faster, 15 hertz, and then 16 hertz on the thulium. You see a little bit more pronounced difference on this particular test between the thulium and the Holmium. Again, less burn back on the thulium. And then finally, on the last graph, we've looked at quite a number of different settings. 1.5 joules, so fairly high energy on the Holmium, 2 joules on the thulium, and then we looked at some low energy, I believe it's 0.1 joule at 600 hertz, and then 6 joules at 10 hertz. So pretty consistently, there was less burn back with the thulium fiber as compared to the Holmium. What's interesting here is, for the most part, you're seeing more burn back as you go up in the joules. So as you make or set a higher pulse energy, you're going to get more burn back, and that is consistent. What we've seen in our research previously with Holmium YAG laser fibers is that is one of the key variables for burn back. So when you treat stones with dusting settings, you tend to get a lot less burn back, even if you crank up the hertz. And as soon as you go to fragmenting settings, we always see that those fibers burn back quicker. And that's pretty much what we saw here with the thulium as well. I would say the one outlier would maybe be that very far right graph, 6 joules. We didn't see maybe as much burn back as you'd expect although the frequency is a bit lower. But typically, as you crank up that energy, you're going to get more. I think the take-home message here is all laser fibers are going to have some burn back, no matter what. So I think the thulium sets itself up well. It's pretty resistant to it. But I think in some cases, depending on your settings, you're still going to get some burn back. So I think it's not a reasonable expectation to say you're never going to see burn back. You potentially are, but I think it's going to be less than what you're used to. So that kind of takes us through some of the science and some of the research that we did before that. So now we're going to spend just a little bit of time looking at some videos of some clinical cases that we did with the SOLTIVE SuperPulsed thulium fiber laser when we had it at Ohio State. And I picked out a couple of videos that tried to answer a few questions. And the first one was, again, this kind of concept of, well, does the thulium work well for hard stones? And we were lucky enough to have a few cases where we had some really hard stones. And I think Brian's going to flip over to the video here. So this first case is a large stone that we did ureteroscopically, 1,400 Hounsfield units on the CT. And what's interesting is if you look at the settings here, 0.05 joules. So not 0.5 joules, which would be a typical setting you'd use on the Holmium, but we're at 0.05 joules, 400 hertz for most of this video. So it really goes to show like how efficiently this stone or this laser can break up this hard stone. There's a lot of headroom to actually go up higher in the settings. Here we briefly went to 0.1 at 200. And I would say we're getting a little bit more of a dust cloud there effect as you're using that setting. You almost get this sort of vortex effect that's created. And then we're going back here to 0.05 again. And again, you kind of see how those pieces start to bounce around. And what you do here is you just hover that laser fiber there and you just let it work. And what you'll find is the pieces just get consistently smaller. They get broken up, kind of ground down. And you're going to see that it sort of spins around a little bit. You see all that dust being created. And then you start to see that you're getting these fragments. And when you look at this, you can see for the most part, they're pretty consistent in size. So those are the fragments that had come off the stone. But there's still some pieces of the main stone around yet. So we're going to kind of try and hunt those out yet. So there's a bigger piece. So again here, we're just kind of holding that laser fiber there and just letting it do the work. Activating that laser. And now we're getting towards the end of the case. I've jumped ahead here a little bit, but this just kind of shows, many of those small, really small kind of dust-like, true dust fragments being created. And you can see them just kind of flushing out through that axis sheet, sort of the dust storm coming down.
Dr. Knudsen, we've got a question coming through the Q&A box here. Would you describe SOLTIVE and thulium fiber to be more of a contact laser than a Holmium YAG, less of a contact laser, or it's kind of a mixed response depending on what you're trying to do?
Yeah, you still, at some point that stone and the laser fiber do need to make contact because the water is going to absorb it. But between the irrigation and getting this sort of vortex going, it's kind of that sort of whole pop dusting phenomenon where you're kind of holding it there and the stone is coming into contact with the fiber at times. But a lot of times we don't have to go chasing it. We just kind of let it do the work. And you're going to see that in this next video too. I would say this was still fairly early on with our experience with it, but this was a stone in the upper ureter. And what we started to realize pretty quickly, here we are at 0.1, 200, again, is just keep that laser fiber kind of in the lumen of the ureter. You can see we're not trying to pin the stone down like we normally would with the Holmium. You just kind of keep it in the middle, activate the laser, and let it do its work. There's a little bit of movement of the stone there, probably from the irrigation, but you can see like all of a sudden all those pieces are getting small and activated a little bit more, and more small pieces. And I really think it's changed our technique in terms of how we handle stones in the ureter. So instead of just going in and splitting them, fragmenting them, and pulling them out, our technique now is just to go in, activate the laser, turn them into dust. Don't use a stone basket, use less disposables, and just let the laser do the work. And it's incredibly fast. And even for distal stones, where you'd go in with a semi-rigid, we started doing the same technique. Just kind of hover in front of it, stay in the lumen, stay well away from the wall of the ureter, and let the laser do the work. So when you get a chance to use this laser, I encourage you to try that technique. We found it really worked well, incredibly fast. You just get in and get out. And we think we're going to be stenting a lot less patients because of that. So one of the areas that I'm quite interested in, and my practice has evolved over the last number of years, is in terms of how I do my perks. So we're doing probably 80% of our perks now are mini perks, and we're doing most of them supine as well. So really, we've been trying to fine-tune our technique, find what works best for us. We had been using Holmium up to it, so we wanted to see how the Thulium worked for the mini perk. So this is a patient had multiple 1 centimeter stones in the kidney, or 3 or 4 of them, and we opted to just go in and use the Thulium to try and break up these stones. So that's probably a 1.2 centimeter stone there. Not very hard, only about 600 Hounsfield units. 0.2 joules, 100 hertz. So again, pretty conservative settings. We've gone quite a bit higher on the frequency since then as we got more and more comfortable with this laser. But you can see, a big stone like that, we're just melting it, cutting right through it with the Thulium. But what you don't see in the video that's probably the most impressive is how much of this stone is actually just washing out alongside our scope as we're doing this. So normally we would expect a whole bunch of pieces at the end. Here, we washed a few of them out, but by the end of the case, this is us inspecting the kidney. And this is how it looked after treating 3 or 4 of these good-sized stones. There's really nothing left. The patient has no fragments to pass. And at the end, we said, well, if it looks like this, we're not going to stent them. We do some of these totally tubeless. We're not going to leave a nephrostomy tube. We're just going to do it completely tubeless, and the patient gets the win out of it. So they get stone-free, and they don't have a tube after. So I really think for mini perks, this is going to be the technique to use. That was a couple of the stones caught on a CT image before. So one of the things I just wanted to briefly touch on, because there are 2 different systems. There's the SolTive Pro system and the SolTive Premium, and I'm sure your Olympus folks will talk to you about them. But the biggest difference really is the difference in what the maximum pulse frequency is. So on the Pro system, it goes up to 100 hertz. So when we looked at that mini perk video, we were at 100 hertz. So clearly 100 hertz still works extremely well to break up stones. But the premium system goes up to 2,400 hertz. So when you start to get into really wanting to use these higher frequencies, and we were using 500 hertz at times on some of the mini perks. The premium system is really the one that's capable of doing that. So it's important to kind of understand that difference. The Pro system will work extremely well. You'll still be able to do a great job with your stones. But if you're really interested in the high frequency, that's where the premium system has that high frequency capability. So just to kind of summarize some of the stuff we talked about tonight. So we saw that the bench performance for the Thulium was really as good or better than basically the top of the line Moses laser systems. So we had better ablation and fragmentation. I hope I covered the safety side of it well, because that's a question that came up a lot. But watts are watts, and the safety profile of the Thulium fiber is really comparable to Holmium YAG. In terms of retropulsion and fiber burn back, it performs extremely well, really on par or better than what the Holmium has to offer. And then, to me, this is such a huge deal, is the small footprint and the quiet operation. If the performance of the Thulium was exactly the same as the Moses, just having a smaller laser that uses a standard outlet and is quiet, to me, is a huge win. Now, you kind of couple that with the fact that it's actually much more efficient and works better than the Holmium on top of it. It's really not even a fair fight. And I think the other part that's really interesting is what this laser might do in terms of innovation in urology in general. So now, urologists have always been creative people, and now you've got a laser that you can take kind of anywhere. You can take it to your clinic. So I think it's going to open up more procedures. I'm certainly going to be treating bladder stones in some of my older patients in the office with it. I think it'd be very easy, very fast to do that. And then it's also going to open up, this whole new avenue of smaller diameter laser fibers. And it's going to be interesting to see where that goes, because maybe we're going to end up with smaller scopes or smaller instruments, because now we can use smaller fibers with it. So I'm very curious over the next number of years, as this technology rolls out, how it impacts the future of endourology. And I think with that, I hope I covered a lot for you and provided some good information. And what I'd really like to do is try and answer some of your questions. I'm sure you guys have some, and I'd love to kind of give you my opinion on it.
Yes, we do have the questions piling up. Great job, Dr. Knudsen. So let's get to them. So one of the questions that came about a few minutes ago, can you think of any single application for stone, in parentheses, not for tissue, in which a Moses Holmium YAG system is better clinically or in the lab compared to a SolTive system?
So far, none that I've encountered. I would say I haven't treated a lot of large bladder stones yet. I would expect that the Thulium would work extremely well for that too, based on my experience with PCNL. So that would probably be one area where I haven't evaluated it myself. But I would say, there's no reason not to expect it to kind of paint and drill through those stones just as efficiently as we saw on the PCNL.
Another question here, how is the stabilization / retropulsion on high hertz compared to Moses technology from your experience? Certainly the lab data covers the side-by-side of virtually no retropulsion, but how did you actually find it clinically?
Yeah, very similar. I think Moses is a good laser in terms of retropulsion. I think people who have used it have noticed a big difference, especially compared to short pulse. And my experience with the Thulium is very similar. There's always going to be a little bit. You're not going to have zero retropulsion, but generally the stones are very stable. And I would say most of the stone movement now that we get is actually from our irrigation, more so than the actual laser energy.
Another good question here about a different indication. Is anybody trying this fiber for HOLEP so far, and if yes, what are the results?
So I have very limited experience with it for HOLEP. I only did one case with it to date. I think Mitch Humphreys, Mayo Scottsdale, he does a lot more HOLEPs than I do and has maybe a little bit more. The big difference is the way this laser cuts. So with the Holmium, you get much more of sort of that blast effect, which can be good, which can be bad. So for instance, if you're cutting a stricture, or I did several cases where I had an infundibular stenosis, the Thulium was really great for that because it's a really smooth, precise cut, but it is very, very hemostatic. Whereas when I normally would do like a diverticulum or an infundibular stenosis with the Holmium, it's always a bit of a pain because it kind of blasts the tissue. You sometimes open up a bleeder that's hard to get to. On the prostate, depending on how you're trained, a lot of people are used to that kind of blast effect or tissue separation effect with the Holmium. It kind of helps open up that plane. With the Thulium, it's a much cleaner cut. So you have to be very confident in your planes. And it's a different feel, and it would be something you would have to try and see how you like it. That being said, internationally, the Thulium really has been used extensively for BPH. The experience in Russia, which is a Thulium fiber laser, slightly different than the Olympus one. They're doing a ton of BPH, and they love it for that. But it is a different feel, so would encourage you to try it and see how you like it.
Have you gotten away from using access sheaths because of the dusting capabilities, or do you find it helpful for irrigating out fragments and visualization?
Yeah, that's a really good question, and it's still something we're wrestling with a little bit, because I really personally would love to move towards less and less stents. We all know that stents are the thing that patients like the least from what we do stone-wise. And I think we have the potential to do that with the Thulium because of how well it does dust. But, the fact of the matter is if you have a big stone up in the kidney and you're dusting it, you're creating a lot of dust, at some point it's going to be pretty tough to see if you don't have very good outflow. And in some situations, you're going to have to put an access sheath up to get that outflow. And in my mind, if you're using an access sheath, especially in a previously unstented patient, you do have to leave a stent after. But in a lot of these, kind of mid-sized stones, where we maybe traditionally had used a sheath, I think now there's situations where we're definitely going to get away from it. And the reason is we're going to be up there shorter with the Thulium because it's going to be faster to break up the stone, and we're going to be more confident that the pieces after are smaller.
We have questions coming in about fiber durability. So what was your experience outside of burn back with the fiber durability of Soltive, and then particularly with the smaller sizes and the 150 micron, I think is piquing everyone's interest as far as how small it is and its durability.
Yeah, we didn't do a lot with the 150. We did a lot with the 200. And to me, I think the 200 is still kind of the sweet spot. It's really, really flexible still. You still get really good flow with our current ureteroscopes. So to me, that's still kind of the go-to fiber. I think if you had a really difficult stone to reach, where maybe you were losing a little bit of deflection, or you've got an older scope that doesn't have the best deflection, the 150 may help. But I think in a lot of cases with our current technology, the 200 kind of seemed to be the sweet spot in terms of pretty limited burn back, but still having enough flexibility to get to where we want to go.
So plenty of good questions here. So here's a two-parter. Have you or are you using this technology for small tumor ablation or endothelioma ablation? And then what are your experiences with thermal damage to the ureteral side of the wall or tissue if the laser fiber touches off to the side?
So I don't do cancer at Ohio State. We have a huge bladder cancer team. I They are very excited about being able to use the thulium for tumors and are talking about wanting to do on-block resections. So I think that's going to be in the cards in the future for us at Ohio State. But I don't personally have experience using it. I think it's going to work great. If on-block resection starts to take off, because again, think of it a little bit like a lightsaber. It's that real precise cut cutting through the tissue, and I would think that's what you're going to want when you're, taking a tumor out on block, as opposed to kind of having that blast effect with the Holmium. So I think that's going to be a situation where it's going to work extremely well. The second part of the question about damaging the ureteral sidewall, if you put that laser fiber in contact with the sidewall and activate it, you're going to get some damage, whether you use a Holmium or a Thulium. So you still have to be wary of that. That's why I'm excited about what I was showing in that one video, sort of that technique of being able to really hover that laser fiber in the lumen of the ureter and get it to work and just stay away from the wall altogether. As opposed to the technique I typically use with the Holmium, which is really to pin the stone down even in the ureter and just split it into pieces. I think that if you're not careful and you keep your foot on the pedal too long, it's very easy to touch the ureteral wall. So I think just by the whole technique of getting that fiber in the lumen and activating that laser, we're going to see that we're going to have less damage to the ureter because of it.
So two questions that are related that I will ask in a sequence. So do you think this technology will allow us to better treat lower pole stones ureteroscopically? And then secondly, are you doing less PCNLs as a result?
So lower pole stones are always going to be challenging cases, no matter what. I think having smaller fragments at the end is going to be a benefit, but I would still, even with the thulium, I would still encourage people to try and displace the stones out of the lower pole if possible. I think that's just good technique. If you can move a stone to the upper pole and leave the fragments in the upper pole, from everything we know from older studies, that's still going to be of a benefit. But if you have a stone that you can't get out of the lower pole and you can get the scope and the laser on it, this is probably going to give you your best shot at getting it cleared. But there's still a chance some of those fragments could settle out. And, future clinical studies will probably tease out the exact percentages and things. But I think the same principles of doing good surgery and trying to move as much out of the lower pole as possible is important. In terms of practice patterns, I think it's going to depend on the individual. I have really, hedged my bets on mini perk. I really think that's been a great technique, and I find the thulium works extremely well with that. That being said, if I have cases where I don't want to do a perk on them, or if it's a borderline stone, we'll have a discussion with the patient, and we certainly can do it ureteroscopically with the thulium as well. So I think it's just more options for the patient and ultimately their choice. I would say, with the way we do our mini perks, we do a lot of them now totally tubeless, or we simply leave the stent overnight and pull it the next morning. So I'd say we send more people home without stents than we do with ureteroscopy. But again, with the thulium, I think we're going to be leaving less stents.
Have you run into residual fragments on post-op imaging, or have you been able to completely treat every stone you've tried it on?
So I think, we've followed our patients that we've treated, but we haven't been CTing everybody. So if you really want to answer that question, you probably need to be CTing everybody at, 2 months after the procedure. And currently our practice is KUBs and renal ultrasounds, unless it's being specifically followed in a study. We're happy with our results. We're going to be presenting, we'll see if we're going to be presenting them at the AUA, if the AUA goes ahead or not. But we are presenting the first series from us, from Kansas, and from Mayo, sort of our early experience and early follow-up for both ureteroscopy, and we're also going to have a PCNL series that's presented there. So we'll have the most up-to-date data for the AUA to talk about. But the results look good. It looks very promising.
In your opinion, what are the limitations of the laser?
I mean, you still, have to be comfortable with ureteroscopy. You still got to be able to get to the stone. But I don't know if there's really limitations. I think it's I don't know. It's a tough question to answer. I would say there really isn't a limitation. It's just kind of advancing what we have. So it's the same issues you have with the Holmium. You still got to be able to get the scope on up to the kidney, up to the stone, and you got to be able to get the fiber onto the stone. But once you do that, it definitely works extremely well. And we haven't run into situations where it doesn't break down the stone. And I think it addresses a lot of the limitations that we have with the
Another question here. So if my hospital has planned a planned budgeted purchase of a high-powered Holmium YAG laser like a Moses, should I have them reconsider with SolTive?
Yeah, if you're looking at investing big dollars into a laser, I think you're doing yourself a disservice by not looking at the technology, because you may end up with buyer's remorse when you see the Thulium in action and you've just spent a lot of money on a Moses laser. It works incredibly well for stones, and I would encourage anyone who's seriously looking at a new capital purchase for a piece of equipment that you're going to have for years, take a look at this laser, because I think it's probably going to change.
A lot of questions here that we're not going to get to tonight, unfortunately. We're just about the end of our talk. I guess one last question regarding short pulse, medium pulse, and long pulse. What is your observation with trying the different modes and adjusting the pulse width? What's the effect on stone and tissue, and what do you recommend?
So the nice thing on the laser console is the defaults are quite good. So the way they're set up, there's super fine dusting and fine dusting. And I would really encourage people to start with those settings when you get it in your hands, and then go from there. It depends a little bit on your technique. Personally, I like to go up on the hertz a little bit, more so than the pulse energy. So I'll usually keep the pulse energy low so that we're getting very small fragments, and then I start to dial up the hertz. And like in the kidney, where you have a lot of room and it's safe and you have lots of irrigation, then I'll really start to crank up the hertz. In terms of the pulse duration, you have to remember there are some differences in the technology, and the short pulse on the Thulium behaves much more like a really long pulse on the Holmium. So it's very different. And because of that, you don't get that same, with short pulse on the Holmium, you kind of get that movement of the stone and when you activate it, and you don't get that. It's a very different feel. So I would say start with the short pulse on the Thulium, and then you could go to some of the longer modes. But a lot of times the short pulse works extremely
A couple of other clinical questions I'd love to sneak in before we sign off tonight. I certainly want to be respectful of the hour. Can you coagulate tissue with bleeding with Soltive? And then another one, what was the highest hertz setting you used? Is there any noticeable difference between 500 hertz and, say, 2,000 hertz?
Yeah, we never went up to 2,000 yet. Just haven't found the need. So I would say the upper end is probably in the 500-600 range, from what I can remember from the cases that I did with it, and that would have been during mini PERT where we went up that high. Maybe on big bladder stones, but again, I haven't treated a lot of big bladder stones with it yet. But there may be a role because I know with Moses, I'll really crank it up in the bladder. So I would probably expect to do the same with the Thulium. But it'll be interesting. I think it's going to require a little bit more study, both clinically and bench, to really fine-tune and optimize the settings. It really took 10, 15 years before people were really starting to fine-tune the settings on the Holmium. Early on, everybody used 1 and 10 for years, and it was only later that people started to figure out what different settings did. So I think we're already ahead of the curve a little bit with the Thulium, but I think there's still room. I mean, this is early days, so I think there's going to be a lot of work that's going to be done on really fine-tuning.
Great, well said. So we are a few minutes past 8:30. I want to thank Dr. Knudsen for his time. My apologies if you asked a question and you weren't able to get it answered tonight. There are a fair amount of questions around pricing, specifically of the capital and the fibers of Soltive. Please work with your local Olympus rep if you have any questions on the pricing of it. It is really dependent on the contract that you're eligible for, that your provider is eligible for. I will say that we don't want pricing to be a barrier to adoption of this great technology that will advance lithotripsy and endourology forward. So it will definitely be a cost savings relative to the higher end, high-powered Holmium YAG lasers today, both in terms of capital price and fiber pricing. But please work with your Olympus representative on that. Dr. Knudsen, outstanding job. We all learned a lot tonight, and thank you so much for your contributions to this project.
Yeah, you're welcome. And, if any individuals feel like they have a lot of other questions, you can get in contact with me. I'm happy to talk to you.
Excellent. Thank you again, and have a great evening, everybody. Thank you for joining.
Thank you. Have a great night, everyone.